Hi, the topic for today is polynomial approximations. Let's review finding tangent lines and using them to approximate the function near the point of tangency. Here's an example. We want to find the line tangent to the curve defined by y equals ln x at x equals e. We'll use that line to estimate ln2. To find the equation of a line, we need two things, a point and a slope. First, let's find the point. When x is e, y is ln e, which is 1. So our point is e, 1. Second, differentiate and evaluate at the location of interest. The derivative is 1 over x. At e, it's 1 over e. We now have the slope. Let's use point-slope form. Y minus 1 equals the slope, 1 over e, times x minus e. Add the 1 to both sides, and we have a very useful form for estimating y values. The equation is y equals 1 over e times the quantity x minus e plus 1. This one can be simplified to y equals x over e. Finally, substitute 2 in for x. ln 2 is approximately 2 over e. 2 over e is 2.7-ish. So 2 over e is more than 2/3. Let's see, 2 over 2.5 is 4/5. 2 over e is more than 2/3 and less than 4/5. Let's take a look at the graph. X equals e is graphed in red. The tangent line is blue. The line is above. It overestimates ln2. Hold on. We don't need the graph to tell us the line overestimates. Do you remember? The second derivative tells us. The derivative of 1 over x is negative 1 over x squared. That's negative between 2 and e, and in fact, everywhere in the domain. The ln graph is concave down, so a tangent line overestimates. ln2 is about 0.69315. 2 over e is about 0.73576. Is that close? How close? Let's be quantitative, scientific even, and calculate our percent error. Let's take the difference, 2 over e minus ln2, divide by the known value, ln2, and multiply by 100%. The second derivative tells us 2 over e is greater than ln2. In this case, we can compare the estimate to the actual value. We're about 6% above. A tangent line is a first degree polynomial. So we just did a first degree polynomial approximation. In our example, the slope, 1 over e, is multiplied by the quantity, x minus e, plus the function evaluated at e. For a general function, f, at a particular x location, a, the first degree polynomial approximation is the slope, f primed at a, times x minus a, plus the function at a. Suppose we used a second degree polynomial. Wouldn't we get closer to the value we want? Okay, let's revise the example. This time we'll use a second degree polynomial. How would a second degree approximation work? The tangent line had the same value and the same slope. What if we matched the value, the slope, and the second derivative at e? Then the second degree poly would have the same concavity at e. It would curve down too. A second degree poly has a square term, a linear term, and a constant. It's all about how close we are to the reference point, e. We can center the mathematical description at e by expressing the polynomial in terms of the quantity x minus e. Let's name the coefficients a with subscripts that match the exponent of the term. Differentiate, differentiate again. Notice, the derivative of the inside function, x minus e, is just 1. Evaluate the poly at e. The first two terms go to 0. Equate to ln e. A sub 0 is 1. Evaluate the derivative at e. The first term goes to 0. Equate to the derivative of ln x at e. That's 1 over e. A sub 1 equals 1 over e. The second derivative equals negative 1 over e squared. So, a sub 2 is 1/2 times negative 1 over e squared. The second degree polynomial becomes, wait, our tangent line is still there. We have one new term and the tangent line we had before. Let's take a look at the new graph. Look how much closer the pink curve is to ln x. It matches pretty well from x equals 1.5-ish up to x equals 4. Estimating ln 2 with a second degree gives us an answer that's about 1% low. We went from 6% high with the line to 1% low with the quadratic. Here's our second degree approximation. We have 1/2 y double prime at e times the square of the quantity x minus e plus y prime at e times x minus e plus ln e. In generalizing, for a function f at a, 1/2 f double prime at a times x minus a squared plus f prime at a times x minus a plus f at a. Okay, where did that 1/2 factor come from? Remember, we differentiated a square term. Imagine using a third-degree polynomial to approximate f at a. We could match the value of the function and its first, second, and now third derivative at a. At a, all but the last term in each expression is 0. Nice. Setting the poly and its derivatives equal to the function and its derivatives at a, we get the coefficients of a third-degree polynomial approximation for f. It has the same value and first three derivatives at location a. Notice the 1/6 factor. Where did it come from? We differentiated a cube, and then a square, and then a linear to get a constant. That's 3 times 2 times 1, 3 factorial. Solving for a sub 3, we had to divide by 3 factorial. And the 1/2 in a sub 2, we differentiated a square and then a linear. 2 times 1 is 2 factorial. And solving, we divided by 2 factorial. For our example, the green curve represents the third-degree approximation. The curve stays pretty darn close to ln x, from x equals 1 to 5. The approximation for ln2 is less than 0.2% high. 0.2%. Holy moly. Here is the nth degree approximation for f at a. The nth term has a coefficient of 1 over n factorial times the nth derivative of f at a. The superscript in parentheses refers to a derivative. If it's f with the superscript 3 in parentheses, it's the third derivative. A sub 2, the coefficient of the square term, is 1 over 2 factorial times the second derivative at a. A sub 5, the coefficient of the fifth power term, is 1 over 5 factorial times the fifth derivative at a. A sub 0, the constant term, is f of a. You could say it's the 0th derivative divided by 0 factorial. By the way, 0 factorial is 1. But that's another story. In general, the jth coefficient is 1 over j factorial times the jth derivative evaluated at a.